Hey, Justin, looks like we've got a few folks already looking to join us for this talk tonight. How are you doing where you're sitting?
I'm doing pretty well. How are you?
Doing good. Weather's holding out nice here, but we had some thunderstorms come through the last couple of days, but that's what living in New England is like.
No storms in California.
Oh, yeah. It looks like we got folks joining from all over the place here. All right, well, let's get started here. I want to welcome everyone today to our Future of Data Meetup. Today's Future Data Meetup is going to be on analytics on time. I'll get into that, what that means in a moment. My name is David Dickman. Hello, glad to see you all here. I'm a director of product management here at Cloudera. My core responsibilities are around SQL and visualization tools for the data warehouse, how to get that data to help you make those decisions. And joining with me today is Justin Hayes, who will introduce himself in a moment. Today, what we want to talk to you about is really fast-moving data. How do we handle real-time data in a data warehouse so we can get analytics on not just what's happening in the stream right now today, but how we can build on that with data that's already happened to give you that kind of predictive analytics that you need to be able to say, hey, given what's happened and what's happening now, what's probably going to happen next? So this is real-time analytics in a nutshell. And be able to see us here on LinkedIn and on Twitter and on YouTube. So wherever you're joining us today, glad to see you here. And feel free to be interactive with us. Ask those questions. We'll be monitoring those questions. And at the end of the session, your questions will be answered. And you're going to want to be asking those questions because we're going to have a raffle. When we have this raffle, if you are asking questions, your name's going to be automatically entered, and we'll do a random drawing at the end of the session. The first name we pick will win first place prize, and you'll see these 4 fabulous items that will now be yours. And the second name we draw will win our second place prize, which is an additional 4 fabulous items that I'm sure you are all eager to get your hands on and enjoy. So absolutely ask those questions, but stick around for the answers, because in order to win these prizes at the end of the session, you have to be present to win. So what I'd like to do now is introduce you to our speaker for the day. Justin, feel free to introduce yourself to these good folks who've joined us here.
Hi, everyone. Thanks for joining. My name is Justin Hayes. I'm in the product management team here at Cloudera. Been with the company just under 8 years now. So that's sort of a old person in the context of the big data ecosystem. I focus primarily on the products within our portfolio that deal with fast-moving data, fast-moving analytics, interactive SQL querying, and things like that. And also, I focus a lot on our cloud service, Cloudera Data Warehouse Cloud Service. So very much in my wheelhouse is the type of use case that we'll be talking about today, which is real-time data warehousing, or how to, like David mentioned, how to string data in and do your analytics and reporting on it pretty much immediately, regardless of the volume. So I'll talk a lot more about that later on, but again, thanks for joining us.
Awesome. Thank you so much, Justin. So looking forward to your presentation and your demonstration. Feel free to take it away.
All right. So I want to get started with some hypotheticals here, a couple questions to get the creative juices flowing here in everyone's heads. So I'm going to use the term a lot today, real-time data warehousing. So I'll try to describe a little bit what that means to us here at Cloudera. The use cases that this refers to are probably fairly well known out there. So just putting a first hypothetical out there, like what if you could have your high performance dashboards that everyone loves with huge data sets that are being queried, but the data is really only just a couple seconds old, right? There's not a multi-hour or day lag between you can query it. So your decision makers can be more effective. They can see what's going on and like right now. So a lot of times latencies are too high, like end-to-end latencies from when the data was generated, whether it's in a source database system or IoT sensor or anything in between. And so by the time that data gets to the decision makers, it can be stale, right? So you're not capitalizing enough on your streaming investments of moving that data around in real time in the first place, because you can't get it in the hands of the decision makers soon enough. What if you could build these pipelines that are much simpler, right? That aren't as complex, that aren't as you're not jumping through as many hoops to apply the updates or to be able to blend together the data that's happening in real time or near real time with all the historical data. So traditionally, if you've done a lot of work in the big data ecosystem, the architectures for getting any sort of real time or near real time analytics and reporting, like out of huge volumes of data, like you end up with some pretty awkward architectures that might work, but they're pretty complex to build and cumbersome to keep running. And finally, if your users, like what if they could get good performance on all types of queries? A lot of times we see a system that's really good for just random access, but terrible for analytics. Really good for slice and dice style OLAP explorations, but really bad for ad hoc SQL exploration where you don't know the patterns in advance, right? Really good for giant batch feature engineering style workloads, but you can't go grab a specific record for some regulatory reporting reason, for instance, things like that. So like having all these patterns in a very self-service manner that's good for both developers, your SQL types, as well as your point and click types all in one place, that's a pretty powerful thing. But a lot of times that's hard to do today because most tools are good at one, maybe two of these different patterns, but not all of them. So like sort of taken all together, this is a sort of a description of what I mean when I say real-time data warehousing. And I want to explore that a little bit today with who it matters to, what it means for the business, how to build these types of applications quickly and easily, but at the same time, such that they'll scale and perform, right? So the first dimension of this we'll look at is who this really matters to, right? Let's never forget the actual people who us technologists are doing work for. So those on the analyst side are decision makers. Typically, they're out in a line of business. Right? A lot of them are tasked with transforming their business, with becoming more data driven or digitizing their operations. And for them, having this immediate insight into operational data is just you can't understate the importance of or overstate the importance of having that capability. And this is true whether you're a bank or a telco or a manufacturing company or anything in between. Good views of data that's timely, where it's again, it's not yesterday's data, it's 2 seconds ago data. Like that's very critical. And also quality of the insights that come out of that. A lot of times it's not enough to just see what happened in the last 2 seconds, 2 minutes. You need to correlate that with what happened yesterday or last year, right? You need to blend that in with other data that might not be time series in nature or coming from some operational data source, but maybe it's clickstream data from your web app, or maybe it's some sort of other marketing campaign related data. But blending that all together is how you can both correlate the data that you're seeing now, as well as enrich it with a broader perspective of what the data is really telling you. And again, it helps make the decision makers, their lives a lot easier. There's an example I'll give in a couple slides of that really brings this to life, I think. Then on the flip side, it's the data developers that are the ones that need to provide this capability to those decision maker end users. They tend to care about, they get asked to provide some report or build some new data pipeline, some new source of data came up we want to tap into. Like, give it to me yesterday, right? And it can't cost too much. So for these folks, the simplicity of the application, simplicity of the architecture is really paramount, because the simpler the implementation, typically the faster it is to build, the lower the skill sets are required, and that's really important. So we can bring more and more people more easily to the party to work on these problems, and easier to maintain, right? And this has to be, because we're talking about streaming data as well as analytics and warehousing, combination of both development of streaming ingest pipelines, and that's typically one type of developer, we'll say, and then what we'll call your data warehouse developer or power user that understands the reporting and analytics side of things. Sometimes they're the same person or the same team, but sometimes they're different. But regardless, it has to be easy and self-service to develop these type of applications, regardless of which end of the spectrum you're on. So that that's why this sort of application, and anything we can do to make it easier is really important to these two different categories of users. And I want to spend a little time talking about specific examples, like use case examples that are common. And again, these tend to be across industry, but I'll call out a couple of our customers that are doing these different specific types of use cases within this real-time data warehousing category to, again, try to bring it to life. So one of which is real-time metrics aggregations. So this is where you typically have a whole bunch of data coming in, and you're keeping the raw data because you need to be able to query at the very fine-grained level, but you're also frequently and constantly updating aggregations and roll-ups and KPIs. You're effectively building a giant OLAP cube, multi-dimensional OLAP cube. So once you're going to show the reports or the dashboards or explore the data, you can, again, get access to the raw, but you can also just do simple reads of all that pre-computed data. So that's sort of a standard OLAP style use case. A great example we have is an ad tech company in the US. They're like a provider, like a broker for matching up people who have websites or mobile apps that can serve out digital ad impressions with advertising providers. And so there's just every day they just run thousands of campaigns for their end customers that basically do digital ad impressions, and they track all of those impressions and every time an ad is clicked and did it convert through, and that just generates billions of data points every day. And what they do is they store all that raw data, but also are just constantly all day long calculating these aggregate data points at a very granular level per campaign and per customer level, so that their thousands of customers can have self-service reporting and analytics and exploration of the data that's specific to what they're doing. So one neat data point here is they do upserts on 1 billion records per day, which is how they can provide this, in a lot of cases, pre-computed data for their end users just constantly throughout the day. It's real value add to their end users. Another example we tend to see is operational reporting on CDC streams. So CDC, that's when you're sort of listening in on an operational database. Maybe it's your CRM system or ERP system. The database is serving out your website, your service layer, things like that. And the streams of transactions that are happening, someone buys something, someone clicks on a certain page, someone updates their address, just constantly streamed into the warehouse, so that you can have reporting done on that that's just very, very much happening in real time. And so this sort of thing, it's very powerful because it effectively mirrors your operational systems in your warehouse. So you can get good views of what's going on in those operational systems without slowing them down by doing the reporting on the source systems themselves. A great example here is a US auto manufacturer. They had a fairly complex batch, mini batch style pipeline where they're doing this historically, and just the time it would take to go and take the next batch of CDC, the transaction log of the transactions that happen, and apply the updates or inserts or deletes, and then update the data down in the warehouse. The shortest time they could get was about 4 hours. And switching over to an architecture that's pretty much what I'll be showing later today in the demo, got 50x latency improvement on end-to-end just by having a more semantically rich set of tools they use in their pipeline, so they didn't have to have as complex and cumbersome of an ingest pipeline, all of which adds up to latencies between when the data happens and when someone can report on it. And another one, this is one I mentioned earlier that brings it to life, this idea of blending together live data with historical data. So this is a big telco in Asia that is a couple years into their 5G rollout. And from day one on that, they wanted to build in a lot of data capability to be more effective at servicing their customers, as well as at reducing the cost of their operations. So what they do is they capture very, very fine-grained data about what's happening on their network and their 5G network. And this is everything from the actual devices on the network, how they're operating, through to logs for what their users are doing. who's calling who's loading, getting data packets from which endpoint, things like that. Then that all comes in at the tune of about 300 terabytes per day of raw data. And then sort of like in that first case, what they're just constantly updating metrics that are calculated at the per customer level. So all their customers that are subscribers to that telco. And then they make that data available to the customer experience management folks, like in the call center, so that when a customer calls up, they've got all the historical, all the times you've topped up your SIM card or bought a prepaid contract or whatever, bought a new phone. And then right that is, here's what's happened in the last 10 minutes of this user's experience actually on the network. Here's the calls they made, here's the calls that got dropped, here's the packets that got dropped when they were trying to load a website or something. And that really arms the customer service representatives with a really rich and timely set of information to better service the customer, again, in very real time. And that's only possible by blending the now with the past, so to speak. Excuse me. Okay, so that's a lot of slides, a lot of words to try to characterize the space that I'm talking about, this real-time data warehousing space. And there's some approaches that have been taken to try to solve for this sort of use case historically. I want to talk through some of those and some of the challenges that those have. So like the most naive way, of course, to do this is just dump it all into a single RDBMS. This might work well for small data volumes, not a lot of complexity in the architecture, but typically this it doesn't scale very well. Think like throw it into a MySQL or an Oracle or a Postgres or something. It's good to get you started, but it certainly won't scale, and it's not very flexible. Another approach that typically happens here, it's your standard traditional data warehousing approach. So here you do get better scale from before, and because there's different steps in, you can handle different types of data sets. Because you land the data into typically an operational data store that's just mirroring the source systems, do your transformations, dump it into the like sort of single source of truth, the gold schema. Then you got your data marts that are specific to different usage purposes. So you do get some flexibility in there, but it's a fairly complex architecture with lots of hops. And all that sort of goes together to increase the end-to-end latency. This is sort of like what that auto manufacturer was doing a little bit. All the different steps needed to be able to just get the logic implemented to change the data around as needed, but also the time it would take to do each step is what added up to those several hours of latency. And you have a duplication of data in different layers as well, which can be an issue at very large scale. So then we'll fast forward through to the big data era, right? Around the mid 2000s, people started playing around with the Hadoop ecosystem, and certainly throughout the last decade, and found different creative ways to deal with this sort of situation. You saw Lambda architectures come up as a way to have the fast lane as well as the slow lane, and then you had to join those together at query time. It got the job done. This is the depiction at the bottom of that. It got the job done, but it's somewhat difficult to maintain that. Other approaches are, let's just rewrite entire partitions of data if you have an update that comes in. And what that means is a lot of operational systems, they'll be sending data in, but it's not just insert only. It's not just new transactions that happen, right? It's someone might change addresses. You need to update their record. So then there might be data correction that upstream system, they calculated the data wrong, and they downstream into the warehouse, they need it reflected there. So whenever there's updates, traditionally that's a hard thing to do because there's no mutability in the warehouse. You had to go in and update entire partitions, which basically you're rewriting a lot of data unnecessarily. And then a lot of times you'd end up with small files, the dreaded yet pervasive small file problem that's been around for a while. And so people would have to run manual compactions. So the point I'm getting at is there's approaches to try to get access to the now as well as the historical all in one place. And there's been approaches to be able to have updates for when the data is changing. And there's been approaches to deal with the fact that you can end up with lots and lots of small files, which has a lot of metadata overhead and inefficient at the disk level. And so all that, again, that conspires to lead to complex architectures that adds latencies. It's easy for things to break. It's hard to add on new sources and things like that. So, of course, you probably guessed by now that I'm going to propose an architecture and a product capability within Cloudera that helps simplify that. Right, and so I'll talk about what that is, but I'm sure everyone's tired of hearing me talk for now. So I'm switch over to demo mode, and I'll show this, and then come back to do some more slides to wrap it up. But before we jump over into the demo, I'm going to give you a preview. So this is my very awkwardly named real-time reporting and analytics on an unlimited number of source operational databases application. You'll see what that means a little bit later. But effectively what's happening is there's a data source. In our case, it's a MySQL database. We have a CDC tool there that's capturing the transactions that get applied within the MySQL. So think of this as it's the database that's sitting underneath our CRM system that's processing all of the orders our customers make, all of where they live, the fulfillment of those orders. Maybe it's got our supply chain information in it. So, all of our operational stuff on which we run the business. We're going to stream that in via NiFi into the Kudu storage layer. And then that happens just immediately. And then we'll query it for reporting purposes, both operational style, like what's happening right now. Where's show me everybody who lives in a specific zip code so I can show them these digital ads, for instance. And also combine that with what's happened historically. So I can maybe structure my next ad campaign more effectively because I'm able to look at historical performance of how ad campaigns went for this specific city, for this specific product, or something like that. So that's what I'll show, and I'll come back to explore some of the specific technical components of this later on after the demo. But for now, I'm going to get out of slide mode. And where this is running, this is a cluster that's running CDP private cloud base. So this is, for those of you that might have used CDH or HTTP in the past, this is a similar form factor, so a single cluster form factor. And it's running in our internal data center that we use here at Cloudera. And I'll be showing a couple of different UIs that are running within the cluster. I'm going to refresh these guys. Great. So first, I'm gonna sort of start with the NiFi flow. If those of you aren't familiar with NiFi, it's a tool for data integration, data movement. It makes it easy to get data from A to B, send it through step C, do a bit of processing on the way, and integrate it, dump it back onto a message bus, and then stick in a database. Like those applications that are really dealing with moving data around can be pretty complex to build. NiFi makes it easy to build those applications and manage them. So ours is pretty simple, and it's like that on purpose. So I'll start with the first part of it. So consume Kafka record. So I mentioned earlier that there's this MySQL database that has the CDC transaction log that's getting streamed out. That's actually getting dumped into a Kafka topic. Now I'll show you some of the Kafka stuff here in a second, but the first part of this data flow, we're just consuming straight out of the Kafka. So in NiFi, you set up these data flows, and in each processor, you configure with the different parameters needed to do whatever it needs to do. So in this one, it's just as simple as pointing at the processor to the Kafka broker, which topic name we want to use. So we see a star here. I'll zoom in a little bit. This is basically saying any topic that matches this pattern. And that's important. Effectively multiplex multiple topics into a single NiFi flow, which simplifies the application and makes this whole thing, again, easier to build, easier to manage. So it's pretty simple and straightforward. That's really the main thing here, is just point it to the Kafka topic. All right, so let me just switch over. We'll explore the Kafka side of things a little bit. So the first thing I'll call out, I don't want to go to the topic yet, is Kafka Connect. So this is a way to really easily provide and run data producers that need to produce into a Kafka topic and consumers that read off of that topic. So in our case, we've got this connector. It's something from a open source project called Debezium that captures CDC logs from a variety of databases, and then in our case dumps it onto a Kafka topic. So what we've done is we submitted this. It's a jar file that Debezium provides that you can configure it with source information for how to connect your MySQL database, submit it into Kafka Connect, and you can do that via this SNM, Streams Messaging Manager UI, or you can do it programmatically. I'd use a curl command to do it. It's just easier. And then all of a sudden from there, we now just have almost automatically the ability to stream out the logs of transactions that happen within that MySQL database onto the Kafka topic that we specify. So, I mean, there's not a lot to see here. It's sort of it's a nice management tool to see how this Kafka Connect producer has been performing over time. So you can see the settings here. This is the JSON that configured it that I submitted originally. And then once that's up and running and doing its thing, any transaction that happens in that source database will result in messages getting sent through into the Kafka topic that we will subsequently consume. So let's look at one of the examples. You can see here, DB server 1, that's just the logical name I gave. And inventory is the database name, and then products, customers, orders, and addresses, 4 different tables. Right, so I mentioned that the pattern is dbserver1.inventory.star that we'll be reading from. That's how we're able to do the multiplexing of messages. I'm going to come here. I don't want to dwell a lot on the Kafka side of things, but I'm just going to show an example. I'm going to leave this up. This is definitely a dense eye chart here, but I'm going to come back to this in a moment. So I just want to leave this up to come back. We'll refer to the messages and see how we're using the data that's in these messages really intelligently to simplify the application. All right, so that's the Kafka side. I zoomed in too much here. What do we do with those messages once we grab them? So we're going to do this, what's called partition record. This is basically a way to apply a little bit of lightweight processing onto one of the records that come through so that we can use that information later on. And specifically, we're going to extract one piece of data from within that record. It's just a giant JSON that's been sort of minified. We want to get this /payload/source/table and store that as this table name variable. Right, so I'm going to come back to this message here. Ignore the first one of these table that we find, but the second one here, table addresses. So if this was on the orders table, this would of course been orders, or customers would have been customers. So what we're doing is we're introspecting the actual data itself to figure out which table we need to ultimately dump this into. Right, and then we store that. We remember that with the flow of processing that happens for this record. And then next we'll come to the put Kudu processor. This is the one that dumps the data into the Kudu table. And I'll explain more about Kudu in a moment. And that's just our fast analytics storage engine that we're using here. So here is similar to the Kafka one. We point it to in this case, the Kudu masters. So this is like the master server for the Kudu cluster. And then the table name here, we're using this parameter that we had defined earlier in that previous step. So this is how we complete that multiplexing that I mentioned. So you don't have to make one of these for each of the 5 tables, or if we would have 50 or 100, right? It's just that the same single data flow can handle all the different tables. So the next thing I'll really call out here is this operation record path. What we're doing here is, again, we are inspecting the message and specifically looking at this payload that's basically pointed at that JSON, and then op. This is the operation that was applied in the original transaction in that MySQL database. If we come back here, let's search for op. There's a lot of them. Anyway, it's this last one. So here, this means it was an update. So this was me earlier doing update, label addresses, set, blah, 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 blah. This resulted in one message that flowed out onto the Kafka topic that was subsequently picked up by NiFi. And in looking at that, I said, okay, it's a U. There's a regex here. We need to use the update ignore operation when we're applying this into Kudu. What that means is update with this data that's encapsulated in this message, do a Kudu update operation, and ignore it fails. Right? This ignore thing is important because in this type of use case, these operations can be idempotent, which means if you run them multiple times, it's okay. Like if you insert ignore, if you get multiple messages coming in, it won't. Second time it won't insert it. It will have already inserted it. Same with delete. It's already deleted. It's already there. Certain types of applications take advantage of this this characteristic of the data, this idempotent characteristic, to again simplify the applications. So that's about it. Literally, that's it. We've got tables created, and Kudu tables are created that will be subsequently be querying, but that's it for we'll say the ingest pipeline part of this. So I'll switch over now to the actual warehouse side of things. So this is Hue. This is our tool for SQL developers, and we'll say SQL friendly analysts who like to get in and do a bit of coding instead of just clicking around on a screen. And I've got a bunch of saved queries here. So the first thing I'll do is I just want to describe, actually let me blow this thing out. Sorry, wrong one. Actually, now's probably a good time. I'm going to switch over to, this is the MySQL CLI. I just wanted to show real quick, there's 5 tables here in the database: addresses, customers, orders, products on hand. I didn't want to spend too much time on this part of it because it's sort of boring command line stuff, but we've mirrored that same table structure out here. So we'll be looking at the addresses table in our queries today. So I just wanted to make that very clear that we've got a one-for-one mapping between the source and then here in our real-time data warehouse. So let me put that away. I want to first do a describe extended on this table. So here what you see is it's just the fields. And then table openers. So this is if anybody's used Kudu, it's just a different storage engine that you can use for the tables in your warehouse. So you have to point it to the Kudu master. So this is that same Kudu master server that we pointed to earlier. And then this the name of the table within the Kudu namespace. So you don't need to worry much about the specifics of Kudu if you don't know about that. But I did just want to point out that this is, now that we're using Kudu as a storage layer here, you can think of this as almost like a real-time table, real-time warehouse table. And there's other types of tables I'll explain here in a little bit that are more historical in nature. So, we'll run this. Right, pretty straightforward. Right now, this is an exact mirror of what's existing in that MySQL database. And then I'm going to do the traditional run a query here, check the results out there. So I'm going to add a record into this MySQL database. What will happen is that Debezium connector is tailing the transaction log. It'll take that, send a message through to Kafka. It'll be picked up by the NiFi and immediately applied into the Kudu database. And I'm querying it now here. So I just added this record, right? Something in North Carolina. It's the most boring thing in the world, right? I mean, it's just all of a sudden it's here. But the fact that it's boring and it works is that's the whole point of it. I'll point out here that it also works when we're talking about tens of terabytes of data per day, and we're talking about 100 node clusters that are needed to process all of that and query on all that in parallel. So the fact that it works now on my simple cluster and the fact that it works on scale, those are at scale. Those are 2 important points. Well, I'll do another thing. I want to do an update here, just to reiterate that. This also means that I changed the city to Raleigh here. So this is going to come in pretty big in the next section, which is I want to join this data that's happening right now, right? Happening in the now with historical data. So we've got another database in the warehouse. It's in the default one. It's web logs. So this is just sort of like clickstream information that came out of Apache web logs from Apache web server. Pretty standard stuff. So this one, it's a parquet table that's stored in HDFS. This is like a standard what you would do for your warehouse within the Hadoop ecosystem, whether it's Parquet or Org or Avro or whatever. It's a typical warehouse kind of table format. And I mentioned earlier a couple times, it's important to be able to blend together the data that's happening now with the data that's happened in the past. It might be in a different part of the warehouse. So again, this one, it's sort of underwhelming once the results come back, but it's pretty important to note that what we're doing here is we're combining these two different types of tables all in one system. And this talks to the variety of query patterns, whether it's primary key-based lookups or very highly selective queries through to large-scale analytic scans, through to calculation and then subsequent querying of pre-computed aggregates, ad hoc expiration. All of those patterns can be satisfied because we've got really the breadth of the entire warehouse at our disposal in terms of different types of files that can handle different table types. That's one of my plugins telling me to update. What I'll do here to sort of reiterate this point is this is the query profile viewer thing that's built into Hue. It's really nice to troubleshoot queries and see what's going on. So just this is a nice way to reiterate that we're combining both HDFS and Kudu source data into one query that presents a single result back to the end user. And this is exactly how that telco in APAC, in Asia, can do the things it does to empower their customer service representatives to be more customer friendly. So that's it on the demo. I'm going to switch back and do a little bit more time talking about some of the technical underpinnings of this. And then there's probably some questions that came out of the demo that hopefully you guys are asking, and we can talk about it at the tail end of this. Okay, so architecturally, this is sort of like the happy path, the simplest way that this type of real-time data warehouse architecture runs. You've got a bunch of sources, and you got an integration layer and orchestration. A lot of times it's batch, a lot of times it's streaming, a lot of times it's both. And we're just dumping that straight into the fast storage and queried immediately. I showed Hue, could be our data viz visualization tool, it could be a third-party BI. So this is what I mean by a simple architecture, right? There's no fast lane, slow lane, there's no processing that's needed to come back and apply updates later on and do your compactions to get good performance. It's all sort of a one-shot deal straight into the end user. That's how we can have that short end-to-end latency. Usually, though, what will happen is people will add on different steps to do different things that might be useful. First thing that tends come on is some amount of stream processing. Maybe you want to enrich the data a little bit, or trigger an alert, for instance. Another thing they tend to do is add on some batch processing. I mentioned earlier that micro batches to build and maintain your aggregates for those KPIs. You're just keeping updated at a very granular level. Maybe you're doing extracts to populated data or something like that. Another one that's very common is blending in this fast operational reporting style data with other data in the warehouse. I showed an example of that, but a lot of times it's done for data tiering purposes. So you have your hot data and your cold data. You store the cold data once it's no longer needs updates, or it's queried as frequently, move that off into HDFS or object storage, and then just join it at query time so the users don't know the difference. But now you're able to basically have a lot deeper storage at a more different cost economics behind it. And then very common, because we're keeping that raw data, and we might also be keeping some pre-aggregated, pre-computed aggregates, and folks tend to like that. They love getting at the raw data. So we can service them pretty well also. And again, give them the real-time data as well as the historical data. So these are just different flavors that tend to get added on. What does this look like in terms of technology? I showed NiFi, of course. Kafka is pretty universal these days in terms of messaging bus to move data around. Spark streaming has traditionally been the most common tool that's used for stream processing, stream analytics, although Apache Flink now is picking up a lot of stream, and there's a lot of really rich semantics in its toolkit that it can bring to these types of use cases. So we're starting to see that show up more and more. Typical Spark and high batch processing. Usually it's Parquet for that if you do need the long-term storage. And then I showed Impala wearing the Kudu for the fast storage. So I talked through a lot of this already, and I want to come back to, this is the version that I showed in the demo. And it's very important to note that I described this verbose application on purpose, right? It's the real-time aspect is important. It's both reporting and analytics you can do. Unlimited number of source operational databases, where that talks to the multiplexing. Send it all through one NiFi data flow. All of that was built with this. About 50 lines of config stuff. This is copying jar files around. That curl command to submit the Bezium connector into Kafka Connect. Some stuff in MySQL to turn on transaction log and things like that. And then 6 lines of DDL to create those tables in the target database. So under 60 lines of code is what gave that application that I just showed. Certainly, for a production one, you probably want to put in some more error handling and things like that in your NiFi flow. But the point stands. Like, this is a pretty powerful application that was built very simply. And the simpler an application is, typically the easier it is to manage. So I already talked about a lot of this. Kafka, NiFi, and SMM, Streams Messaging Manager. These are the tools for our streaming and data integration. So not a lot of code and configs, as you saw, but a lot of functionality. And specifically on the management side, with the NiFi, NiFi UI, then the SMM UI, it's very easy to manage these, especially the upstream portions of these applications, which are notoriously hard to administer and manage once you're in production. And then the core engines for storage and querying, Apache Kudu and Apache Impala, mentioned those a lot. They're what really allow for the simplicity of the application, the mutability, so you don't have to go back and rewrite entire partitions. Doing upserts and ignores, so you don't have to have a lot of conditions in your ingest pipelines. To, if this is, like I showed you that regex that was sort of one nested regex that turned the specific operation into the specific Kudu operation. Like, that could be whole different branches of code if you were doing this in Spark, for instance, and you didn't have mutability of the source data, or the target database, which is Kudu. Apache Kudu is also great for handling multiple query patterns, whether it's very selective, either random access or very small ranges of data, all the way through to really heavyweight analytics scan style data. And it's got really a lot of partitioning flexibility, so you can match the partitions that are used for the tables through to the use case at hand. So that lets you prevent hotspotting, for instance, at write time. It lets you parallelize your reads really effectively. It lets you balance between, I want to, all my data has a time element, so I want to keep the most recent data sort of fresh in memory, but I want to roll off old data really effectively without having to truncate the whole table. So there's a lot of capabilities on the partitioning side that, like semantic richness you have on the partitioning side that lets you get good performance, especially at scale. Then I showed Hue for the SQL development. I won't dwell much on that anymore. I did not show data visualization. This is our UI. This is one of the point-and-click tool that I alluded to earlier. So this is sort of a traditional visualization dashboard style tool that lets you really easily build your visualizations of data that exists in a warehouse, and also create semantic layers that are perhaps more relevant to the end users that might not know the source data model really well. They just know that they want to make their data look a certain way so their subsequent reporting and communication with their colleagues is easier. Having a layer where you can apply that semantic modeling almost is really powerful and helps democratize access to the data to a much broader set of users. So the data viz tool is definitely a big topic that if you're interested in, we can go deeper on that in a future session, but that's something that really helps with the ease of use for the end users. And then workload manager, I didn't show this. This is a tool for tuning and troubleshooting our queries. Again, it's all about democratizing the ability to improve performance of the queries that are running in the warehouse. So you don't need a really expert power user to interpret an Impala query profile, for instance, or your Hive metrics and figure out what's going on. So all of these are all about self-service tools to get easier for the end users, but also offload the burden of the teams that are managing the warehouse and building applications in the first place. Okay, key takeaways, and then we're going to move on to the Q&A section in a moment. But first off, for the business analysts and decision makers, so these are the ones, they at the end of the day just need to operate more effectively. Right? Typically, this means they need more immediate insights from their data, more visibility into the data that's happening now. They need to correlate it with the historical data as well, so they make sure it's the right insights they're getting. And they don't want to jump from lots of one system to the next to be able to handle all the ways they need to ask questions of the data. And then the developers, it makes it easier for them to build these sort of applications that satisfy the business users and the decision makers. So as you saw, not a lot of code and configuration for a pretty powerful application. All of that goes through to make it reduce TCO, simpler to support, and easier to build, so you don't have to find that unicorn developer that happens to know all this stuff to be able to get these apps built. All right, with that, I'll hand it back over to David, who's going to facilitate the Q&A, and I'll be here to answer the questions as they come in.
Awesome. Thank you, Justin. That was a really great demo. And we got a couple of questions that have come in. And got one here that's come in that's asking, oftentimes I need to compare my current state against the historical. Does Cloudera let me both do an iterative query of the most recent data and also be able to go back in time and look at data that's happened before?
Yeah, so there's two approaches, well, a couple of approaches actually. The short answer, yes. A lot of times what we found is, unless we're talking about just absolutely gigantic data scales like petabyte plus, a lot of our customers just leave the data in that Kudu storage layer, which gives that like immediate sort of real-time querying, and it also has all the historical data. It can handle very, very large volumes. So there it's sort of like the one table holds all the data, right? So there's nothing you really have to do there. You get it for free, so to speak. We have some cases where the addressable data is bigger than that, and what'll happen is they will move out older data, say after it becomes a year old or a month old, or pick your time frame, move that out from the Kudu table and store it in a Parquet back table, right? So two different tables, one which has say the data from now until a year ago, and the other one that has data from a year and a day ago all the way back to the start of time. And then at query time, you can actually create a view that joins those together. So the end users, whether it's someone writing a SQL query or just building a dashboard, they just query the one table, and behind the scenes, it actually transparently knows how to go to each of those sort of base tables to get the data as needed based on maybe the timestamp and the where clause or something like that. So yeah, short answer, yes, and there's different reasons why you might do that, and we can handle all the different cases.
Excellent. And just want to remind folks that are listening to us here, if you want to win those prizes, we'd love to see your name start showing up and fill out our contestants list a little more. We do have a couple more questions that we can go through, but I just want to make sure that everybody who's out there listening wants a chance to win those prizes and also wants a chance to get your question answered. We're here and waiting to get those. So here's another question. So got another question here. This is about storing data in Cloudera Data Platform. The question is, do you force data to be stored in a proprietary format?
No, so none of the formats that we can even handle are proprietary. So everything we have is both at the file format level, as well as the table type level, as well as the actual engines. They're all open source. They're all Apache open source. Typically at the format level, we have Apache Parquet, Apache Org, Avro. Sometimes it's text, CSV, things like that. But for the most part, for the warehousing context, it's Parquet, Org, sometimes Avro. Those are just completely open source and very well supported across the entire ecosystem. And then like the Kudu, I've obviously been talking a lot about that. There is, you can think of Kudu, it's like, there's not a file format there, it's actually an active storage engine. And so there's no like Parquet file format within the Kudu table. But what you have is open APIs. So Apache Kudu, I showed you the Impala integration where you're not actually talking to Kudu, you're just running Impala queries that just behind the scenes talk to Kudu, but there's Spark API for Kudu, there's Java and a Python API. So even at the engine levels, my point is that there's nothing proprietary going on there. So your data is never locked away. It's always open for you to use as you need.
Cool. One more question here. If we put together a system similar to the one that you demonstrated, could you update operation? Could the update or CDC operations be implemented in Spark if the storage engine used is Kudu?
Yes, if I understand that right. In fact, that's done today as well. There's people that will take the CDC, like the transaction logs will usually they'll flow onto a message bus and they'll be picked up. So it's common for them to land on the Kafka or something else, and then use Spark streaming to sort of do micro batch processing of those. And maybe you're applying some amount of transformations in those Spark streaming jobs or maintaining rolling window of something, and then write it directly into Kudu. So the Spark Kudu integration is very, very well hardened. It's been around for many, many years. It's a very common thing to do. And that's true whether it's, again, like Spark streaming micro batch or just standard Spark core batch. So yeah, that's absolutely possible. What I would say is the latency is where you got to pay attention. Even with micro batch with Spark streaming, depending on how big your micro batch windows are and how much processing is going on, that, you know, if you need the data to be queryable within 2 seconds or 1 second of landing in a Kafka topic, anything you do to add latency can take away from that. But there's nothing functional that prevents you from using Spark to do this sort of processing of that CDC stream and then saving it into the Kudu table.
Excellent. So here's another one. It's coming from a YouTube user who's asking, are there any examples of PhoenixDB in usage? And I'm not sure if they're asking any examples of PhoenixDB in usage at Cloudera or usage in a real-time analytics situation.
I'm going to assume that PhoenixDB is referring to the Phoenix that's a SQL engine, SQL layer on top of HBase. Mm-hmm. There might be something called PhoenixDB that's separate that I don't know about. But in that case, what I would say is, so Phoenix is good for making it easier to build HBase applications because you sort of live you can interact via SQL, so the secondary indexes, all that sort of stuff. It makes it a lot easier to work with HBase. So from that perspective, it's a great tool. It's also you're able to do some amount of operational reporting and analytics using Phoenix, but at the end of the day, HBase is really optimized for random access and sort of small scale range scans. And if you're doing any large analytics style queries where you're scanning a lot of data, maybe calculating some statistical value over a long history of data, HBase is not optimized for that sort of access pattern. And so the end result is certain query patterns just won't work very well with HBase as the storage layer versus with Kudu as a storage layer, because Kudu was created to be able to do both the random access, very selective queries, as well as the big heavyweight analytics scan style queries.
Right.
So there's a little bit of overlap, but not a lot, I guess, is the short answer.
Cool. Well, I have a couple more questions coming in. So one is, can you explain the different things that are done when you add in the stream processing layer as you stream data into the data warehouse. So I think we're going back to that chart that you'd shown where you had a solid line and then an optional path. So what does that stream processing layer help give us?
Yeah, I mean, so it's a simple, I mean, you could, the thing I showed actually, there was some tiny amount of stream processing to do that multiplexing, which was looking at the message and figuring out what the source table name was. And then we subsequently use that to decide where to write it into Kudu. So something as simple as a little bit of almost like routing of traffic, or maybe changing a data type or a column name in a small, like, let's say, simple processing. That can happen all the way through to deriving new columns. So maybe we've got, I'm thinking of an example, maybe we've got biometric information for people that might have their age. Maybe we, as data, that's just whatever to capture the source system. We want to segment them into age ranges like 0 to 10, 10 to 20, 10 to 30, etc. You might want to, as the data is coming in, derive a field that automatically assigns the right age range. That second, this other field based on their specific age. So that's an example of deriving new columns, new columns, new fields. You might drop fields. You might maintain, and this happens a lot. I think I alluded to it earlier with Spark streaming, and I know this is done in Flink as well. But maintain a rolling count. So like for the last 5 minutes, how many drop calls were there? Let's count those up, and then we'll save that alongside whenever we write that out to the resulting Kudu database. So like lightweight statistics calculation that happens in the stream. Mm-hmm. And then, there's some people do reporting, triggering, like if a certain threshold has been surpassed, and maybe it's one of those rolling windows, or maybe a message came in that had a super high reading from some sensor out there, send a message somewhere to go be handled. So that kind of thing happens. So we see the range, I guess, of different types of things that are done. But for the most part, it tends to be just a bit of data cleanup, a bit of enrichment, maybe normalization, and all the country names into the ISO country code, things like that.
Cool. I think we got time for another question or two. Does the point-and-click user have the ability to select to join the data in the Kudu tables with random other tables that they have access to across CDP, or does that have to be pre-configured?
Absolutely. Well, it does not have to be pre-configured. Absolutely, they can do that. So at the end of the day, with that data visualization tool, all it's doing is running queries in the warehouse. The fact that it's an Impala table that happens to have Kudu as the storage engine, and there's another Impala table that happens to have Parquet as the storage layer that's stored in S3, for instance. And maybe there's another table that actually it's an ORC table, like it's a Hive asset table that's also living in S3. Like at the end of the day, those are just tables that the Impala query engine can query. And so the user that's doing visualizations, all they're doing is pointing to each table and saying, I want to select such and such fields, and here are the filters that I want to use, and that gets turned into the necessary query. The fact that it's hitting all these different storage options behind the scenes, that's left as almost an implement. That's a detail for the Impala engine to figure out. The end user, all they see is a table definition. I want these columns and these rows. So it's our goal on purpose to make that seamless and transparent, so the end user doesn't have to know or care about all the internals behind the scenes.
Cool. I think we can squeeze in one last question. And it's an acronym I haven't seen before, but maybe it's familiar to you. Won't SMM help on top of Kafka?
Oh, yeah. SMM, Streams Messaging Manager. That's just like a management tool that is used to administer your Kafka cluster and your topics and your producers and consumers and all that. So that's the second tab that I showed, where we went in and looked at the Kafka Connect thing, where we submitted the Debezium connector. So absolutely, that helps, especially in terms of managing the application. I mentioned earlier, like administering a Kafka cluster when it's meant to be always on. Messages are flowing through at incredibly high throughputs. Operationally, that can be difficult, so we want to make that easier, and that's what SMM is for.
Cool. All right, well, that's all the questions we have right now. So if you folks like this content, for more information, you can visit the Cloudera's users page for videos, tutorials, events, and more at cloudera.com/users. The Cloudera video tour is also available here at this link, where you can explore Cloudera through interactive videos to get a sense of how this product can help you. And also look for more of the Future of Data meetups on the Future Data Meetup page here for you folks at futureofdata-austin on meetup.com. And if you're interested in more meetups like this one, we have the next one coming up: collect, curate, predict, and visualize your data streaming. This will be Thursday, May 20th from 6 to 7:30. And so feel free to attend the next one as well. The link there to join that is right at the bottom of the page. And now we're going to go to the raffle time. So here we get to reward some of the lucky folks who came by and asked us some questions during the session. And let's take a look at who our winners are going to be. We have winner number 1 is going to be, our lucky first place winner is MCCAT. So if your handle is MCCAT, you have won those 4 lovely items that were there for our first prize. And now for our second place winner, we will have Drew Nicolette. Drew, thank you for asking questions as well. You are our second place winner and will also be getting some wonderful prizes. So thank you all for joining. This concludes our meetup. Oh, by the way, you will be contacted from social media at cloudera.com. Reach out to social media at cloudera.com. Email that address if you want to claim your prize. So if you're one of our 2 lucky winners, email us at socialmedia@cloudera.com to claim your prize. So this concludes our meetup. And on behalf of the team, I want to thank everybody for being here. I want to thank Justin for presenting. I want to thank all of you for coming and joining us. I want to thank our fabulous backstage crew for making this work seamlessly and like magic, putting the right things in the right place at the right time. And we look forward to seeing you at the next Future of Data meetup. Thank you for joining us today. Have a great evening, afternoon. Goodbye.